Around 110 million years ago, the center of Australia looked nothing like it does today. Where red desert stretches to the horizon now, there was once a sea, not a lake, not a river system, a sea so large it covered nearly a third of the continent, and at its peak, split Australia into scattered islands. The water was cold, murky, and filled with predators. Its largest hunter was named after a Greek titan who ate his own children. It had teeth the length of a human forearm and hunted other marine reptiles. Elsewhere in the sea, long-necked creatures swallowed smooth stones from hundreds of kilometers away and carried them in their stomachs for reasons scientists still debate. And when this ocean finally disappeared, it left behind one of the strangest fossil records on Earth. In one remarkable discovery, the skeleton of a marine reptile was found almost entirely transformed into opal, complete with the remains of its last meal preserved inside its ribcage. The sea itself is gone, but its water is not. Beneath the Australian desert lies an enormous underground reservoir formed by the rocks this ancient sea left behind, still supplying water across vast parts of the continent today. The Eromanga Sea vanished millions of years ago. Its creatures vanished with it, yet traces of both are still shaping Australia in ways most people never realize. In tonight's journey, we're exploring the lost ocean that once covered the heart of Australia and the extraordinary world it left behind. But before we begin, I'm curious, is this your first time here, or have you been down this rabbit hole with us before? Let me know in the comments. Now, let's follow the shoreline of a sea that no longer exists, far to the south of the world we know. Long before deserts spread across the heart of Australia, the continent occupied a place that seems almost impossible from a modern perspective. Between roughly 110 million and 120 million years ago, during the Cretaceous period, Australia was not standing alone in the ocean. It remained physically joined to Antarctica, part of the last fading architecture of the ancient southern supercontinent known as Gondwana. The land sat much closer to the South Pole than it does today. In southern regions, the yearly rhythm of light and darkness followed a pattern unfamiliar to most modern landscapes. For weeks at a time, the sun remained low or absent, and long stretches of dim polar winter settled across forests and wetlands that occupied latitudes now associated with ice. Yet this was not a frozen world. The atmosphere held far greater concentrations of carbon dioxide and methane than today, trapping warmth across the planet. Average global temperatures may have been as much as 15 degrees Celsius or 59 degrees Fahrenheit, warmer than modern conditions. Permanent polar ice caps had not yet taken hold. Regions that would one day lie beneath vast glaciers instead supported living ecosystems. Forests extended into high southern latitudes, their roots gripping soil that never experienced the crushing weight of continental ice. Across Australia, towering conifers rose above dense expanses of ferns and ancient vegetation. The climate was cool and wet rather than dry. Rainfall moved through broad river systems, feeding floodplains and lowlands. The red interior familiar today did not yet exist. In its place stood a greener landscape shaped by water, forests, and shifting geological forces deep beneath the surface. Those forces were slowly changing the continent from below. As Gondwana began to fragment, immense stresses worked through Earth's crust. Central Australia responded by sagging downward over vast distances. This gradual sinking, known as tectonic subsidence, unfolded so slowly that no living creature could have perceived it. Generation after generation passed while the land continued its descent. Over time, the continent's interior developed into an enormous depression, stretching more than 1,000 kilometers, which is about 621 miles across. At the same moment, the oceans of the world were unusually high. The middle of the Cretaceous period ranks among the greatest high sea level intervals in Earth's history. With little permanent ice locked at the poles, seawater occupied regions that today stand well above modern shorelines. Coastlines around the world shifted inland. Shallow seas expanded across continents. The boundaries between land and ocean became fluid and unstable. In northern Australia, marine waters began advancing through what is now known as the Carpentaria Basin. The movement was gradual but relentless. Salt water pushed southward into the subsiding interior, filling low ground created by millions of years of crustal sagging. What began as scattered marine incursions slowly expanded into something far larger. The ocean entered the continent and found room to stay. Water spread across lowlands, drowned ancient landscapes, and transformed valleys into seaways. New coastlines appeared, while older ones vanished beneath the surface. The depression at the continent's center became a gathering place for the sea, a broad inland realm where marine life would eventually flourish in extraordinary abundance. This was the birth of the Eromanga Sea. Its history would not be a single uninterrupted flood. Over the next 20 million years, the sea would advance and retreat multiple times, reshaping the geography of Australia with each cycle. Shorelines migrated, habitats shifted, and entire ecosystems rose and disappeared with the changing water. The name Eromanga survives today in a small Queensland town. It is thought to derive from an Aboriginal word meaning hot, windy plain. Few names carry a greater contrast. Beneath that modern landscape of heat and dust, once stretched a vast southern sea, gathering its first waters at the bottom of the world. Seen from far above, the outline of Australia would no longer resemble a single continent. Water now occupied so much of the interior that familiar boundaries had dissolved into something fragmented and unfamiliar. The young Eromanga Sea had expanded beyond its beginnings, spreading across an immense portion of the land until its surface covered more than 1 million square kilometers, which is about 386,102 square miles. It was larger than many nations that exist today, a vast inland realm where horizon met horizon with little interruption. Its reach extended across what would one day become Queensland, South Australia, New South Wales, the Northern Territory, and the broad spaces between them. In places, the sea stretched so far that it effectively divided the continent into separate pieces. Highlands that had once been connected became islands. Ancient ridges emerged from the water as isolated chains of elevated ground. Plateaus stood above the flooding like distant archipelagos scattered across a pale southern sea. Life continued on those islands. Dinosaurs moved through forests and wetlands perched above the shoreline, following pathways that no longer led to neighboring lands. Between one island and the next lay broad channels of open water. Some separations reached hundreds of kilometers, which is about hundreds of miles, creating natural barriers that reshaped migration, feeding territories, and the rhythms of daily survival. From a geological perspective, the Eromanga Sea belonged to a special category of ocean. It was an epicontinental sea, sometimes called an epieric sea, meaning that seawater rested directly upon continental crust rather than occupying the deep basins of the open ocean. Beneath its waters lay the same continental foundation that supported forests, rivers, and future deserts. The sea had not replaced the continent, it had settled on top of it. This distinction influenced everything about the environment. Epicontinental seas tend to be broad and shallow. Their margins shift easily. Their character changes with climate, sediment, and sea level. The Eromanga Sea embodied all of these qualities. Across enormous distances, sunlight could still reach toward the seafloor. Rivers carried minerals and sediments into its waters. Shorelines wandered gradually across the landscape as conditions changed over time. Among modern bodies of water, the Baltic Sea offers one of the closest comparisons available to scientists. Though separated by immense spans of time, both environments share certain characteristics. They are relatively shallow. They experience strong environmental fluctuations. Their waters are shaped as much by the surrounding land as by distant oceans. The comparison is not perfect, yet it offers a faint modern reflection of a world otherwise lost. While animals moved across shorelines and islands, another process unfolded beneath them. Layer after layer of sediment drifted downward through the water column. Fine particles settled across the seafloor, accumulating so gradually that each generation of life scarcely altered the pace of deposition. Muds, silts, and mineral-rich sediments spread across the basin floor, preserving a record of changing conditions. Over immense stretches of time, these sediments would become stone. Names familiar to geologists today, the Tulabuk Formation, the Ilaru Mudstone, and the Wallumbilla Formation, were beginning their long journey into existence. What appeared to be ordinary layers of seafloor sediment would eventually become some of the richest fossil archives in the southern hemisphere, preserving traces of entire ecosystems that vanished long before humanity emerged. Human beings did not yet exist. Even the earliest ancestors of humanity remained unimaginably distant in the future. Mammals lived in this world, but they occupied modest roles, small creatures moving through shadows beneath larger forms of life. Across land, sea, and sky, reptiles dominated the age. They filled rivers and forests, coastlines and open waters. The continent beneath the sea continued to change, but for this moment the balance belonged to them, spread across islands and shorelines, surrounding one of the largest inland seas the world had ever known. A map can describe the shape of a sea, but it cannot describe its character. From a distance, the Eromanga Sea might appear familiar, another broad body of water spread across a continent. Yet the closer one moves toward its surface, the stranger it becomes. Nearly every expectation formed by modern images of prehistoric oceans begins to dissolve. The popular imagination often fills ancient seas with brilliant blue water, coral gardens, and warm tropical currents drifting beneath bright skies. The Eromanga Sea belonged to a different world entirely. Its waters occupied southern latitudes close to the polar regions, and that position shaped everything that followed. Despite a greenhouse climate warmed by elevated levels of carbon dioxide and methane, geography still mattered. Sunlight arrived at a lower angle than it did nearer the equator. Winters lingered longer. Seasonal darkness stretched across the southern reaches of the basin. The result was a sea whose temperatures remained surprisingly low. Much of the water likely ranged between 8 degrees Celsius, or 46 degrees Fahrenheit, and 12 degrees Celsius, or 54 degrees Fahrenheit. Conditions resembled the coastal waters of southern England or the fjords of Norway far more than any tropical lagoon. In the far south of the basin, seasonal ice may have appeared during winter months. Thin sheets formed across sheltered regions, then vanished again with the return of spring. The image feels almost misplaced beside the word sea, yet the evidence suggests that parts of this ancient waterway occasionally brushed against freezing conditions. The sea was broad, but it was rarely deep. Most of its waters spread across shallow continental crust, creating a landscape of submerged plains rather than abyssal depths. Geologists estimate a maximum depth of roughly 200 meters, which is about 656 feet, while much of the basin remained considerably shallower. Across enormous distances, the seafloor lay relatively close beneath the surface, creating an environment where small changes in climate or sea level could transform vast areas of habitat. Its connection to the greater ocean was also limited. Narrow marine corridors linked the basin to waters beyond Australia, but these connections were restricted and imperfect. Fresh seawater entered slowly, circulation remained sluggish. Water that arrived in one region could remain there for long periods before mixing fully with surrounding areas. This restricted exchange produced another unusual consequence. Oxygen levels gradually declined in deeper portions of the basin. Near the surface, life still flourished beneath the available light. Farther down, however, replenishment became increasingly difficult. The lower layers grew depleted, creating conditions unlike those found in well-mixed modern oceans. The appearance of the sea reflected this chemistry. Rather than clear blue water, much of the basin likely carried a muted gray-brown color. Rivers flowing from eastern highlands transported immense quantities of sediment into the sea. Among the most important sources was the volcanic terrain associated with the Whitsunday volcanic province. Fine particles eroded from those ancient landscapes, drifted outward through river systems, and remained suspended in the water, limiting visibility and scattering light. Even the air above certain regions may have carried a distinctive character. In oxygen-poor zones, microorganisms processed organic material through chemical pathways that released hydrogen sulfide. This gas is responsible for the familiar scent associated with decaying eggs. Across portions of the basin, especially where circulation weakened, that sulfurous presence may have lingered above the water. Among modern environments, the Baltic Sea offers perhaps the closest comparison. It is shallow, environmentally variable, and influenced heavily by restricted circulation. Researchers have used it as a useful depositional model when studying the Eromanga Basin, not because the two seas were identical, but because they share certain broad ecological tendencies. The result was an inland sea, unlike the warm prehistoric oceans often imagined. Cold water, suspended volcanic sediment, seasonal ice, depleted oxygen, and immense shallow distances combined to create an environment with its own distinct identity, a setting shaped by constraints that would influence every creature living within its boundaries. Far below the surface, beyond the reach of waves and drifting currents, the character of the Eromanga Sea changed once again. Water that seemed merely cold and murky from above concealed a deeper transformation beneath it. Descending through the basin was not simply a journey through depth, it was a gradual passage into a different chemical world. At roughly 30 meters, which is about 98 feet, dissolved oxygen began to diminish sharply. Below that threshold, conditions grew increasingly hostile to the kinds of organisms that dominate most marine environments. Fish could not linger there for long. Large invertebrates found little opportunity to thrive. The familiar communities of complex seafloor life that inhabit many modern oceans were largely absent. Yet the seabed was far from empty. Spread across the mud were immense bacterial mats, living layers of microorganisms adapted to circumstances that would overwhelm most larger creatures. These communities drew energy from sulfur compounds, iron-rich minerals, and decaying organic material settling from the waters above. They occupied a realm where oxygen offered little advantage and where entirely different forms of chemistry governed survival. The seabed functioned almost like a vast biological engine. Each grain of sediment arriving from above became part of a slow cycle of transformation. Organic remains drifted downward from the upper water column. The bacterial mats processed them, breaking compounds apart and rearranging them through countless microscopic reactions. Iron moved through sediments, sulfur circulated through chemical pathways, carbon accumulated within the mud. Over time, the seafloor developed a composition unlike that of many modern tropical seas. The sediment became rich in organic matter, saturated with carbon and infused with iron. Layer after layer settled into place, creating a dark archive of chemical history beneath the water. The consequences of this environment extended far beyond the lives of the organisms inhabiting it. Long after the sea itself disappeared, those ancient sediments would continue changing beneath the continent. Buried ever deeper, compressed beneath younger layers of rock, some of the accumulated organic material would eventually contribute to the formation of petroleum and natural gas deposits. The energy resources later extracted from regions such as the Cooper Basin owe part of their origin to biological productivity that unfolded within these waters over 100 million years ago. The same unusual chemistry also established conditions that would later allow a different transformation to occur. Silica-rich groundwater, oxygen-poor sediments, and the gradual replacement of buried organic structures would create circumstances capable of preserving fossils in remarkable ways. Those events belong to a future separated by immense spans of geological time, yet their foundations were already being prepared on this ancient seabed. For the ecosystem itself, another consequence proved even more important. Death behaved differently here. When an animal died in the upper waters and its body began sinking through the basin, gravity carried it toward a place where decomposition slowed dramatically. In most marine environments, scavengers arrive quickly. Microorganisms consume soft tissues. Currents scatter bones. Skeletons are disarticulated and dispersed long before burial can protect them. The lower reaches of the Eromanga Sea interrupted that process. The oxygen-poor conditions limited the activity of many decomposers. Large scavenging communities were scarce. Sediment accumulated steadily across the bottom, covering remains before they could be extensively disturbed. A carcass entering this environment often experienced a remarkably gentle transition from death to burial. Bones remained where they fell. Skeletons retained their natural arrangement. Delicate structures survived that would normally vanish within days or weeks. Each layer of mud acted as a protective blanket, separating the remains from the dynamic world above. Across millions of years, this process repeated itself countless times. Fish, marine reptiles, invertebrates, and other organisms descended into the basin and became part of its growing record. The same conditions that restricted complex life along the seafloor created one of the most effective natural preservation systems on Earth. What appeared to be a biological wasteland was also an archive. Beneath the cold waters, among bacterial mats and dark sediments rich with iron and carbon, the history of an entire ecosystem settled gently into the mud, waiting for stone to remember it. Movement defined the upper waters of the Eromanga Sea. Countless drifting bodies, darting shapes, floating shells, and suspended clouds of microscopic life occupied every available layer between the surface and the dark chemistry below. What appeared from a distance to be empty water was, in reality, densely inhabited from top to bottom. The foundation of this world was not built by giant reptiles or powerful predators. It rested upon invertebrates, animals without backbones, whose combined abundance supported everything above them. Their remains accumulated in extraordinary numbers across the basin, leaving behind one of the richest records of marine life in the southern hemisphere. Among the most recognizable inhabitants were the ammonites. These cephalopods, distant relatives of modern nautiluses and squid, carried beautifully coiled shells divided into intricate chambers. More than 50 species have been identified from the Tullabuck Formation alone, each preserving subtle differences in shape, ornamentation, and growth pattern. Some were scarcely larger than a human hand. Others reached far greater dimensions, drifting through the water column as active participants in the ecosystem rather than passive floating shells. Their importance extends beyond their lives. Ammonite species appeared and disappeared over relatively brief spans of geological time, allowing their fossils to function as remarkably precise chronological markers. When paleontologists discover a particular ammonite within a rock layer, they often know exactly where that layer belongs within the history of the basin. Entire chapters of Earth's past can be recognized through the curve of a shell. One genus, Australosaurus, occupies a special place within this record. Its distinctive coil appears during a specific interval and serves as a signature of that moment in geological history. Millions of years later, a single fossil shell can still announce the age of the sediment surrounding it. Sharing the water with the ammonites were the belemnites, streamlined cephalopods that resembled squid in life. Hidden within their bodies was a hard internal structure known as a rostrum. These dense supports survived fossilization exceptionally well, and today they are among the most common remains recovered from Eromanga sediments. Vast numbers accumulated across the basin. Their bullet-shaped forms are found so frequently that they have become a defining feature of many fossil sites. Living closer to the seabed were immense populations of bivalves. Among them, Inoceremus occupied a prominent role. These large shellfish formed extensive beds across portions of the basin floor. Layer upon layer of shells accumulated over time, contributing directly to the physical structure of sedimentary deposits that would eventually become stone. In some places, their remains became part of the architecture of the landscape itself. Other creatures occupied every remaining niche. Gastropods grazed and scavenged. Crinoids extended feather-like feeding arms into passing currents, collecting suspended particles from the water. Crustaceans searched the sediment for food. Countless filter feeders extracted nourishment from the nutrient-rich sea. Every available source of energy was being utilized by something. The scale of this abundance is difficult to compare with modern environments. Food existed almost everywhere. Tiny organisms fed larger ones. Larger organisms became prey themselves. Nutrients circulated constantly through the ecosystem, sustaining a remarkably productive marine community despite the unusual conditions of the basin. None of these animals dominate popular illustrations of prehistoric seas. Their names rarely appear in museum headlines, yet they formed the true foundation of the Eromanga ecosystem. Without ammonites, belemnites, shellfish, gastropods, crinoids, and crustaceans, the larger inhabitants of the sea could not exist. Every hunter depended upon them, directly or indirectly. Across the water column, countless lives unfolded simultaneously. Shells drifted through dim currents. Soft-bodied swimmers pursued smaller prey. Feeding structures opened and closed with the movement of the sea. Beneath the surface, energy flowed upward through layer after layer of life, supporting a marine world whose greatest inhabitants owed their existence to this vast and restless swarm. Not every hunter of the Eromanga Sea appeared strange at first glance. Some carried silhouettes that would still be recognizable in modern oceans, shapes refined by hundreds of millions of years of aquatic evolution. Their presence is recorded not through complete skeletons resting in stone, but through scattered fragments left behind across the basin, traces sharp enough to reveal that skilled predators were already moving through these waters. Sharks occupied that role. They patrolled the sea in substantial numbers, particularly members of the group known as lamnid sharks. These ancient relatives belong to the same broad lineage that would eventually produce the great white shark, though the famous predator of modern oceans remained tens of millions of years in the future. The resemblance was one of ancestry rather than identity, yet the familiar design was already emerging. Streamlined bodies, powerful tails, and rows of continually replaced teeth made them efficient hunters in an environment where visibility was often limited. Their bodies present a challenge to the fossil record. Unlike most vertebrates, sharks possess skeletons made primarily of cartilage rather than dense bone. Cartilage performs exceptionally well in life, remaining flexible and lightweight, but it rarely survives the long journey into deep geological time. As a result, complete shark fossils are uncommon. What endure are the hardest structures, especially teeth, and occasionally vertebrae from particularly large individuals. Throughout the rock layers of the Eromanga Basin, these remains appear again and again. Teeth emerge from sediments deposited across different intervals of the sea's history, revealing predators that were not rare visitors, but established inhabitants. Each fossilized tooth marks a life that once moved through cold waters crowded with prey. Taken together, they form a pattern of persistence stretching across millions of years. Yet alongside these familiar hunters lived creatures that seem far more difficult to place within the modern imagination. They are known as chimeroids, often called ratfish or ghost sharks. Despite those common names, they are neither true sharks nor ordinary fish. They belong to an ancient lineage of cartilaginous fishes that diverged from shark ancestors long before the Eromanga Sea existed. Their bodies combined features that appear almost assembled from different animals. Large eyes, elongated heads, wing-like fins, and specialized mouths gave them an appearance unlike anything commonly encountered today. In the modern world, chimeroids survive mostly in deep ocean environments, inhabiting waters far below the reach of sunlight. There they move through dim habitats where pressure is immense and food often arrives slowly. Their preference for such depths makes their presence in the Eromanga Sea particularly intriguing. During the Cretaceous period, these animals inhabited comparatively shallow waters. Some species appear to have reached sizes larger than those of any living chimeroid. Although their complete forms remain elusive, the fossils they left behind provide important clues. Paleontologists most often recover tooth plates, broad grinding structures designed not for slicing flesh, but for crushing hard shells. Fin spines and tiny tooth-like scales embedded in the skin also survive occasionally, offering glimpses of their anatomy. Those tooth plates reveal much about their lifestyle. Across the basin floor lived vast populations of shelled invertebrates. Ammonites drifted through the water. Bivalves occupied dense communities along the seabed. Chimeroids specialized in exploiting this abundance. Their crushing jaws allowed them to break shells that would resist the teeth of many other predators. Their presence also reveals something deeper about the environment itself. Animals now associated with deep marine settings were thriving in a sea that was geographically shallow. The explanation may lie in the unusual combination of low temperatures, dim conditions, and oxygen-depleted waters that characterized much of the basin. In ecological terms, parts of the Eromanga Sea may have resembled modern deep ocean habitats despite lacking great depth. Between the sharks above and the shell-crushing chimeroids below, a middle layer of predators occupied the food web, moving constantly through waters rich with life and opportunity, each adapted to a world unlike any sea existing today. Between the shell-crushing fishes below and the great marine reptiles that would later dominate the sea, existed another tier of hunters, larger, faster, and built from bone rather than cartilage. They occupied an important middle ground within the Eromanga ecosystem, pursuing prey while remaining vulnerable to predators larger than themselves. Their lives reveal a recurring pattern within this ancient sea, a world where success never guaranteed safety. These animals belong to the ray-finned fishes, a group that still dominates modern oceans today. Their descendants fill rivers, lakes, and seas across the planet, yet the species inhabiting the Eromanga Sea possessed forms uniquely adapted to the conditions of their time. Among the most agile were the fishes of the genus Pachyrhizotis. Their bodies resembled modern tunas, streamlined and efficient, designed for active swimming through open water. They remained relatively modest in size, generally under 1 meter in length, which is about 3.3 feet, yet their anatomy reveals a remarkable level of specialization. Two known species demonstrate how evolution can reshape a common design to solve different ecological challenges. One possessed larger and more robust teeth, suited for handling tougher prey. The other carried a narrower snout lined with more slender teeth, better adapted for capturing softer-bodied animals. Both shared the same fundamental body plan, but each occupied a slightly different hunting role. In a crowded ecosystem, even subtle differences could reduce competition and allow closely related species to thrive side by side. Moving closer to the seabed, another predator waded within the dim water. Flinders bore a very different appearance. Reaching lengths of approximately 1.4 meters, which is about 4.6 feet, it resembled an oversized grouper more than a sleek pursuit hunter. Its jaws projected forward in a pronounced underbite, creating a distinctive profile, unlike most fishes of the basin. Thousands of tiny comb-like teeth lined its mouth, forming an efficient apparatus for seizing smaller prey. Rather than relying on speed across long distances, Flinders appears to have favored patience. It likely occupied lower levels of the water column, remaining near the basin floor where reduced visibility offered opportunities for ambush. A sudden burst of movement from concealment could prove more effective than prolonged pursuit. In an environment where suspended sediment limited sight, surprise became a valuable hunting strategy. Yet even these predators were overshadowed by a larger fish that ruled the bony fish community. Kuyu australis was the giant of its kind within the Eromanga Sea, growing between 2.5 kilometers, which is about 1.6 miles, and 3 kilometers, which is about 1.9 miles, in length according to the supplied conversion rule. It represented the largest known ray-finned fish of the basin. Its size placed it among the most imposing fishes of the ecosystem. For many animals, such dimensions might have offered protection. In the Eromanga Sea, size provided only temporary advantages. One of the most important specimens of Kuyu australis, nicknamed Wanda and displayed at Kronosaurus Corner in Richmond, preserves direct evidence of this reality. The fossil bears distinct bite marks embedded within its bones. Their spacing and dimensions correspond closely with the teeth of large marine reptiles that inhabited the basin. The wounds tell a detailed story. Paleontologists have found no evidence of healing around the damaged bone. The fish did not survive the encounter. Whatever attacked it inflicted injuries that proved fatal, leaving behind a rare record of predator and prey preserved within the same skeleton. Such discoveries reveal the underlying logic of the Eromanga ecosystem. Every layer of the food web overlapped with another. Animals hunted while simultaneously being hunted. Success depended upon speed, awareness, timing, and circumstance. Even the largest bony fish remained part of a chain extending upward toward predators capable of overcoming them. Across the cold waters of the basin, these fishes occupied the space between smaller hunters and the marine reptiles that increasingly dominated the upper levels of the food web, forming an essential link in one of the most complex ecosystems of the ancient southern world. If a traveler from the modern world could glimpse one large animal moving through the Eromanga Sea, there is a good chance they would mistake it for a dolphin. The body shape would seem familiar at once, a streamlined form cutting efficiently through the water, propelled by a powerful tail and guided by narrow flippers. Yet, that first impression would conceal an evolutionary story stretching far deeper into the past. The animal was Platypterygius australis, an ichthyosaur. By the time it entered the waters of the Eromanga Sea, its lineage had already spent more than 100 million years adapting to life in the ocean. Its distant ancestors had once walked on land during the Triassic period, breathing air and moving across terrestrial landscapes. Over immense spans of time, those reptilian ancestors returned to the sea and gradually transformed into some of the most specialized marine animals Earth had ever produced. The result was one of the clearest examples of convergent evolution known from the fossil record. Platypterygius australis and modern dolphins arrived at remarkably similar body plans, despite belonging to entirely separate branches of life's history. One descended from marine reptiles, the other emerged from mammals. Their resemblance exists because the demands of rapid swimming shape bodies in predictable ways. Water rewards efficiency, and evolution repeatedly discovers similar solutions. The similarities, however, are only part of the story. A dolphin propels itself by moving its tail up and down. Platypterygius australis generated thrust differently. Its tail moved from side to side, more like a fish than a whale. The distinction appears subtle from afar, yet it reveals the vast evolutionary distance separating the two animals. Beneath a familiar outline existed an entirely different anatomical heritage. Adults reached lengths of approximately 5 meters, which is about 16.4 feet, to 7 meters, which is about 23 feet. Within the Eromanga Sea, this made them among the larger active hunters of the ecosystem. Their bodies were built for sustained movement through open water, capable of covering significant distances in search of food. One feature immediately stands out in their fossils. The eyes were enormous. Relative to body size, ichthyosaurs possessed some of the largest eyes known among vertebrates. In Platypterygius australis, these oversized organs likely provided a major advantage in waters where visibility was frequently limited. Large eyes gather more available light, improving the ability to detect movement and shapes in dim conditions. For a predator navigating through sediment-rich waters, this adaptation may have been essential. Control in the water came from 4 paddle-shaped flippers. These structures were not the primary source of propulsion. The tail supplied most forward movement. Instead, the flippers functioned as sophisticated control surfaces, allowing rapid changes in direction, precise steering, and sudden braking. Studies of the shoulder region indicate a remarkable range of motion. During pursuit, the flippers could alter their angle dramatically, helping the animal pivot through the water with impressive agility. Its diet reflected the abundance of prey available throughout the basin. Fish formed an important component, joined by squid-like animals and belemnites. Evidence for this comes not only from ecological inference, but from direct fossil discoveries. One specimen recovered from South Australia preserved belemnites within the stomach region, suggesting they had been swallowed whole rather than crushed before consumption. Unlike reptiles tied to land, Platypterygius australis never needed to leave the sea. Ichthyosaurs gave birth to live young in the water. Their bodies had become so completely adapted to marine life that returning ashore to lay eggs was no longer possible. Fossils from several ichthyosaur species around the world preserve mothers in the process of giving birth, offering rare glimpses into this fully aquatic existence. The geographic distribution of Platypterygius australis mirrors the reach of the Eromanga Sea itself. Fossils have been discovered across Queensland, New South Wales, South Australia, the Northern Territory, and Western Australia. Wherever the waters extended, this predator appears to have followed. Even today, new discoveries continue emerging from those ancient sediments. In August of 2025, researchers announced a specimen discovered near McKinley in Queensland that may represent the most complete ichthyosaur ever found in Australia, a reminder that the sea still holds many of its stories within stone. Some fossils preserve an animal, others preserve a journey. Among the marine reptiles of the Eromanga Sea, few embody that distinction more completely than Eromangasaurus australis. Its very name is tied to the inland sea it inhabited, meaning the southern Eromanga lizard. Reaching lengths of approximately 10 meters, which is about 32.8 feet, it was one of the most distinctive animals in the ecosystem. Much of that length belonged to a neck so elongated that it seems almost improbable when viewed through modern eyes. Eromangasaurus belonged to the elasmosaur branch of the plesiosaur family. Its body combined features that appear drawn from entirely different creatures. A relatively small head sat at the end of a remarkably long neck. A broad torso occupied the center. 4 large flippers provided locomotion. The result was an animal unlike anything alive today, shaped by evolutionary pathways that vanished tens of millions of years ago. One of the most important specimens ever discovered is housed in the Queensland Museum. It includes the only complete skull known from an Australian elasmosaur. Time has not treated the fossil gently. The skull is heavily crushed, distorted by geological forces acting long after the animal's death. Yet, enough remains to reveal details of anatomy, feeding behavior, and a life spent moving through the cold waters of the basin. The skull also preserves evidence of another story, one written not by geology but by teeth. That evidence rests in the background for now, while attention shifts to a different mystery, the smooth stones that accompanied animals like Eromangasaurus throughout their lives. These stones are known as gastroliths. Fossil discoveries from Queensland elasmosaur relatives confirm that such reptiles deliberately swallowed rounded stones. They were not accidental inclusions gathered while feeding. They were carried within the body, sometimes in substantial numbers. The reason remains a subject of scientific discussion. One possibility involves digestion. The teeth of Eromangasaurus were not designed to crush hard-shelled prey. They were better suited for grasping and holding. Gastroliths may have helped process food after swallowing, functioning in a manner somewhat similar to the grinding stones used by certain modern animals. Another explanation focuses on movement through the water. Stones add weight. By carrying ballast internally, an elasmosaur may have achieved more efficient buoyancy control, maintaining preferred depths with less continuous muscular effort. In a vast sea where energy conservation mattered, even small advantages could become important. The most intriguing detail emerges when the stones themselves are examined. Some gastroliths discovered with Australian elasmosaurs originated far from the places where the animals eventually died. Geological analysis suggests that certain stones traveled more than 300 kilometers, which is about 186 miles, before becoming part of the fossil record. The implication is remarkable. Eromangasaurus was not confined to a small territory. It crossed enormous stretches of the Eromanga Sea during its lifetime, moving between distant regions and carrying physical evidence of those journeys within its own body. Its feeding habits reflect a similarly methodical lifestyle. Fossilized stomach contents from related elasmosaurs reveal a varied menu that included bivalves, gastropods, crinoids, crustaceans, belemnites, and small fish. Rather than specializing in a single prey type, these reptiles appear to have exploited a broad range of resources associated with the seafloor. Their extraordinary necks played a central role in this strategy. Despite frequent artistic depictions, the neck could not bend and coil like that of a serpent. Biomechanical studies indicate limited vertical flexibility. Horizontal movement was more effective. The neck functioned less as a striking weapon and more as a sweeping tool, extending reach across the seabed while the body remained relatively stable. Everything about Eromangasaurus suggests patience rather than speed. It was a traveler, a forager, and a persistent presence moving across the breadth of an inland sea. Yet preserved upon that crushed skull are marks left by another animal, reminders that even a reptile carrying stones from distant shores shared its world with predators capable of reaching it. A thriving sea is measured not by the size of its largest predator, but by the number of different ways life learns to survive within it. Across the waters of the Eromanga Sea, countless ecological roles were already occupied. Hunters pursued prey through open water. Others searched the seabed. Some drifted between habitats, while others specialized so completely that their anatomy became a reflection of a single lifestyle. Among the most remarkable of these specialists was the animal now known as the Richmond polycotylid. Discovered near Richmond in Queensland and housed at Kronosaurus Corner, this marine reptile is regarded as one of the most complete vertebrate fossils ever recovered from Australia. Preservation of such quality is exceptionally uncommon, particularly among marine reptiles whose remains are often scattered before burial. In this case, the skeleton survived with extraordinary completeness, providing a detailed portrait of an agile hunter that once moved through the inland sea. Unlike the long-necked elasmosaurs, the Richmond polycotylid possessed a compact body plan. Its neck was relatively short, its head proportionally larger, and its shape favored speed and maneuverability. 4 powerful flippers worked together to propel and steer the animal through the water with impressive control. It occupied a role similar to that of an active pursuit predator, capable of chasing fish and other mobile prey rather than relying on slow foraging along the seafloor. An intriguing pattern emerges when its anatomy is compared with relatives from other parts of the world. The Richmond polycotylid appears larger than many closely related species found elsewhere. Such differences hint at the influence of local environmental conditions. The Eromanga Sea, despite its unusual chemistry and restricted geography, provided sufficient resources to support larger body sizes even among predators that occupied middle levels of the marine reptile community. Elsewhere within the basin lived another plesiosaur whose most distinctive features were not related to feeding or locomotion at all. Running along its snout and extending above the eyes were delicate crests, unlike those found in other known Eromanga species. These structures were thin, prominent, and unlikely to have provided practical advantages during hunting. Instead, they appear to have functioned as visual signals. Throughout the animal kingdom, display structures evolve for communication. Feathers, antlers, crests, and ornamental features often convey information about health, maturity, or social status. In the dim waters of the Eromanga Sea, Visual recognition may have been particularly important when individuals encountered one another. These crests transformed the animal's head into a display surface, allowing it to stand out against the muted background of suspended sediment and filtered light. Its teeth reveal a different aspect of its lifestyle. Long, slender, and protruding forward, they were not built for crushing shells or tearing large prey. Instead, they appear ideally suited for seizing soft-bodied animals such as fish and squid. Precision replaced brute force. Speed and timing mattered more than raw strength. Marine turtles added another layer of diversity to the ecosystem. At least 4 species are known from the Eromanga Sea, each occupying slightly different habitats. Among them, Notochelone stands out as the most common marine reptile fossil discovered within the basin. Reaching roughly 1 meter in length, which is about 3.3 feet, these turtles appear to have been widespread inhabitants of the sea. Their fossils occur so frequently that they provide a recurring presence throughout the geological record. Larger turtles also shared the environment. Kratachelone occupied a different niche, apparently spending more time in open water than near shore. In this respect, it may have behaved somewhat like modern leatherback turtles, which often remain far from coastal habitats. By utilizing different regions of the same sea, multiple turtle species avoided direct competition while living side by side. Taken together, these animals reveal the true complexity of the Eromanga ecosystem. Swift pursuit hunters, display-adorned specialists, broad-ranging turtles, long-necked foragers, shell-crushing fishes, and countless smaller organisms occupied different depths, diets, and behaviors. Within a shallow inland sea, marked by cold waters and dim horizons, an entire marine world had assembled itself, each species fitting into a place uniquely its own. Long before its full shape emerged from stone, Kronosaurus announced itself through teeth. A fragmentary jaw was discovered near Hughenden in Queensland during the closing years of the 19th century. Embedded within it were 6 enormous teeth, enough to suggest that an animal of unusual proportions once ruled these waters. Decades later, further study allowed paleontologist Heber Longman to formally describe the species and give it a name worthy of its scale. He chose Kronosaurus queenslandicus, honoring Kronos, the titan of Greek mythology famous for swallowing his own children, and the Australian state where the fossil had been found. The choice was fitting. Among the marine reptiles of the Eromanga Sea, Kronosaurus occupied a position unlike any other. It belonged to the pliosaurs, the short-necked branch of the plesiosaur family. Where elasmosaurs invested heavily in reach and endurance, pliosaurs concentrated their anatomy around power. Nearly every feature of Kronosaurus reflects that evolutionary emphasis. Adults reached lengths of approximately 9 meters, which is about 29.5 feet, to 10 meters, which is about 32.8 feet. Estimates of body mass range from roughly 10.6 tons to 12.1 tons. In overall dimensions, the animal approached the size of a modern city bus, though its proportions were radically different. Much of that mass was concentrated toward the front of the body, where an immense skull dominated its silhouette. That skull could reach approximately 2.4 meters in length, which is about 7.9 feet. Even among marine reptiles, such dimensions were extraordinary. The head alone exceeded the length of many entire animals, sharing the same ecosystem. From the tip of the snout to the rear of the jaws, every part was engineered around the ability to seize and overpower large prey. The teeth reveal how this was accomplished. Unlike the blade-edged teeth of many predatory dinosaurs, Kronosaurus possessed large conical teeth designed primarily for gripping and crushing. Some reached lengths of approximately 30 centimeters, which is about 11.8 inches, with crowns measuring roughly 12 centimeters, which is about 4.7 inches. They were not built to slice flesh into neat sections. Instead, they functioned like massive spikes. Once those jaws closed around a target, escape became extremely difficult. Studies of jaw mechanics suggest a bite force somewhere between 15,000 and 27,000 newtons. To place that in context, a large modern saltwater crocodile is capable of generating around 16,000 newtons, already among the most powerful bites found in living animals. Kronosaurus occupied the same range and may have exceeded it substantially. Such force allowed it to attack prey protected by bone, muscle, and thick connective tissue. Yet power alone does not explain its success. Movement through the water depended upon 4 large flippers, each reaching approximately 2 meters in length, which is about 6.6 feet. Rather than paddling like a duck, Kronosaurus used lift-based locomotion. The flippers generated thrust by sweeping through the water in a manner comparable to modern sea turtles and sea lions. This system provided efficiency as well as speed, allowing sustained travel across large portions of the basin. The hunting strategy that emerges from its anatomy is both effective and familiar. In the dim waters of the Eromanga Sea, visibility was often limited. Prey moving above would appear as darker shapes against the brighter surface. A large predator approaching from below could exploit that contrast. Many researchers suspect Kronosaurus employed precisely this tactic, rising upward from the murky depths toward animals silhouetted overhead. Modern great white sharks use a remarkably similar method when attacking prey near the surface. Fossils indicate that Kronosaurus queenslandicus was unique to Australia. At one time, a large pliosaur discovered in Colombia was assigned to the same genus. Subsequent research demonstrated that it belonged to a different lineage entirely and was reassigned to the genus Monquirasaurus. As a result, only a single confirmed species of Kronosaurus remains. Within the Eromanga Sea, that solitary species stood at the summit of the marine food web, an animal whose enormous head, crushing bite, and efficient movement made it one of the most formidable predators of the ancient southern world. Some prehistoric predators earned their reputation through size alone, others through anatomy. Kronosaurus possesses both advantages, yet the strongest case for its dominance comes from something far more persuasive than appearance. The evidence exists in fossilized bone, preserved across millions of years, with a level of detail that allows ancient interactions to be reconstructed long after the sea itself disappeared. The distinction matters because paleontology often works through inference. Teeth suggest diet, limb proportions suggest movement, skull shape suggests behavior. In many cases, researchers assemble a picture from clues rather than direct observation. With Kronosaurus, some of the clues are far more explicit. One line of evidence comes from fossilized stomach contents. Rarely preserved in the fossil record, such remains provide a snapshot of an animal's final meals. In specimens attributed to Kronosaurus, paleontologists have identified the remains of sea turtles and bones belonging to elasmosaurid plesiosaurs. These were not hypothetical prey items inferred from anatomy. They were physically present inside the digestive tract of the predator itself. The implications are straightforward. Kronosaurus was consuming other large marine reptiles. Animals that occupied substantial positions within the ecosystem were themselves becoming food. Yet, an even more revealing category of evidence exists. It appears on the surface of bone. The only known skull of Eromangasaurus, the long-necked elasmosaur discussed earlier, survives in a condition that immediately attracts attention. The fossil is heavily crushed. Geological pressure can certainly deform bones after burial, but skulls of plesiosaurs are often among the more durable elements of the skeleton. Dense bone and robust construction frequently allow them to survive conditions that destroy more delicate structures. The damage present on this skull stands apart from ordinary compression. Embedded within the fossil are bite marks. Their dimensions, spacing, and depth provide a record of the jaws that produced them. Researchers comparing these marks with the known anatomy of Kronosaurus have found a compelling match. The distances between punctures correspond to the arrangement of its teeth. The penetration depth is consistent with large conical crowns. The overall pattern aligns with an animal possessing a skull approximately 2.4 meters long, which is about 7.9 feet, armed with teeth measuring roughly 30 centimeters, which is about 11.8 inches. The conclusion emerging from that evidence is difficult to ignore. Kronosaurus was not restricting itself to fish, squid, or smaller prey. It was attacking Eromangasaurus, one of the largest predators in the sea. The bite marks transform a theoretical interaction into a documented one. Predator and prey are connected directly through traces preserved in stone. The same pattern appears elsewhere throughout the ecosystem. Large kuyu fish preserve injuries attributable to marine reptile attacks. Polycotylid remains carry signs of predation. Turtle shells display scars left by powerful jaws. Across different species and different habitats, the fossil record repeatedly reveals encounters between hunter and hunted. Viewed together, these discoveries reveal something important about the structure of the Eromanga Sea. It was not organized as a simple ladder of life. The ecosystem functioned as an intricate web in which multiple predators overlapped, competed, and sometimes consumed one another. Animals occupying high positions in the food chain still faced danger from larger hunters. Size offered advantages, but it rarely guaranteed safety. The geography of the basin intensified those relationships. The Eromanga Sea maintained only limited connections to the wider ocean through relatively restricted marine passages. Populations remained linked within the same inland marine system for immense spans of time. Predators, prey, competitors, and scavengers shared the same waters generation after generation. Within that enclosed world, evolutionary pressures accumulated steadily. Every successful adaptation invited a counter-adaptation. Every hunting strategy encountered resistance. The marks preserved in fossil bone are the physical record of that long struggle, evidence that life within the Eromanga Sea was shaped not only by climate, chemistry, and geography, but also by millions of years of constant interaction between animals pursuing one another through the cold waters of an ancient inland sea. The sea changed when the light began to leave, not through storms or sudden cooling, but through the slow turning of the planet itself. As months passed and the sun sank lower across southern skies, daylight shortened across the Eromanga Sea. The effect was especially profound in its southern reaches, where the ancient coastline lay at latitudes between approximately 60 degrees south and 80 degrees south, deep within regions that would today be considered part of the Antarctic realm. Modern perceptions of the Cretaceous period often focus on warmth. Forests flourished near the poles. Permanent ice sheets were absent, yet warmth did not erase geography. The Earth still tilted on its axis, and high latitudes still experienced dramatic seasonal swings in illumination. During winter, The southern portions of the Eromanga Sea entered extended intervals of diminished daylight. For weeks, and perhaps months, in the farthest regions, the sun remained low on the horizon or disappeared for prolonged periods. The world did not necessarily descend into complete darkness at all times, but it entered a state of perpetual twilight unlike anything experienced across most inhabited regions of the modern world. For the animals living there, this was not an occasional challenge. The marine reptiles of the Eromanga Sea were residents, not seasonal visitors. They did not migrate thousands of kilometers, which is about 621 miles, to tropical refuges each winter. Their lives unfolded entirely within this high-latitude environment. Every year, they endured the changing rhythm of light and darkness as a permanent feature of existence. The consequences touched every level of the ecosystem. A predator such as Kronosaurus depended heavily on surprise. Earlier clues preserved in anatomy suggest attacks launched from below, where prey would appear as silhouettes against brighter water near the surface. During periods of reduced daylight, however, that contrast weakened. The boundary between shadow and illumination became less distinct. Predator and prey moved through a world where visual certainty was increasingly difficult to achieve. In such conditions, hunting likely relied upon a combination of senses. Subtle movement, pressure changes, and disturbances within the water may have become as important as direct sight. Every passing body generated information. Every stroke of a flipper altered the surrounding fluid environment. The anatomy of Platypterygius offers another clue. Its enormous eyes have long attracted scientific attention. Relative to body size, they rank among the largest known in vertebrate history. Large eyes gather more available light, improving vision in dim conditions. Within a seasonally dark sea filled with suspended sediment, that adaptation becomes easier to understand. Every additional fragment of light carried value. Near the seabed, the challenge grew even greater. Long-necked elasmosaurs, searching for food along the bottom, often operated in regions where visibility was already limited by depth and water quality. During the darker months of the year, vision may have played only a partial role in locating prey. Vibrations traveling through water, chemical traces released by living organisms, and tactile information gathered through movement likely contributed to their ability to navigate and feed. Even the geological record preserves hints of these seasonal changes. Analysis of oxygen isotopes preserved within fossil belemnites recovered from sediments of the Great Artesian Basin reveals evidence of pronounced temperature variation throughout the year. Summers were milder. Winters were cooler. These fluctuations align closely with expectations for a marine environment situated at high southern latitudes. The Eromanga Sea existed within a climate shaped not only by global warmth, but also by strong seasonal cycles. Winter in this inland sea would have been unlike the familiar image of the Mesozoic world. Along southern margins, seasonal ice may have formed during the coldest intervals. Reduced circulation allowed deeper waters to remain stagnant. Sulfur-rich conditions persisted below. Above them, marine reptiles continued their lives beneath dim skies, navigating an environment shaped by darkness as much as by water. The result was a marine ecosystem that feels surprisingly unfamiliar, a high-latitude world where giant predators, ancient fishes, and long-necked reptiles endured months of fading light within one of the most unusual seas Earth has ever known. Not every hunter in the Eromanga ecosystem moved through water. Some traveled upon a different sea entirely, one made of air, wind, and distance, tracing vast circles above the inland waters, while the marine reptiles below remained unaware of their passage. From that elevated realm came the first vertebrates to master powered flight. Pterosaurs had already existed for an immense span of time by the early Cretaceous. Their origins stretched back roughly 230 million years, long before birds appeared and long before bats would eventually evolve. By the time the Eromanga Sea reached its greatest extent, they had become among the most successful flying animals on Earth. One of them patrolled these southern skies. Its shadow drifted across the water's surface, passing over schools of fish, swarms of belemnites, and even the territories of predators far larger than itself. For a brief moment, it could look down upon every creature in the sea, including Kronosaurus. This animal is Haliskia petersoni. The name translates roughly as Peterson's Sea Phantom, derived from ancient Greek words associated with the sea and with a shadowy apparition. It is a fitting name for a creature that spent its life suspended between sky and water, above a world that would eventually vanish beneath stone and desert. Haliskia possessed a wingspan of approximately 4.6 meters, which is about 15.1 feet. Though modest compared with the largest pterosaurs known from later ages, it was still an impressive aerial predator. Its long jaws carried interlocking conical teeth adapted for gripping slippery prey. Fish and squid were likely important components of its diet, and belemnites probably formed another frequent meal. Rather than soaring endlessly far offshore, Haliskia may have spent much of its time following productive feeding grounds where marine life gathered near the surface. A passing fish, a cluster of cephalopods, or a disturbance in the water below could trigger a rapid descent. Its jaws would strike the surface and emerge carrying prey back into the air. For many years, Australia's pterosaurs remained frustratingly elusive. Most species were known only from isolated jaw fragments or scattered bones. Their existence could be confirmed, but their appearance remained largely hidden. That changed in November of 2021. Near Richmond in Outback, Queensland, a remarkable fossil came to light. The discoverer was Kevin Peterson, a former avocado farmer who had later become a curator at Kronosaurus Corner. The specimen he found proved extraordinary by Australian standards. Haliskia is approximately 22% complete, making it more than twice as complete as the only other known partial pterosaur skeleton previously recovered from Australia. Although much of the animal remains missing, what survived provides an unusually detailed glimpse into its anatomy. The fossil preserves complete lower jaws, the tip of the upper jaw, 43 teeth, vertebrae, ribs, bones from both wings, part of a leg, and elements of the throat known collectively as the hyoid apparatus. These throat bones are especially intriguing. They measure roughly 70% of the jaw length, suggesting powerful tongue and throat musculature capable of helping the animal manipulate and swallow active prey. Other clues reveal the stage of life at which the animal died. Several shoulder bones are fused together, a feature associated with skeletal maturity in pterosaurs. Haliskia was not a growing juvenile. It was a fully developed adult, experienced in the routines of hunting and flight. Eventually, its journey ended above the Eromanga Sea. After death, the body settled downward through the water column. Beneath it lay the same oxygen, poor seafloor that had preserved so many other inhabitants of this inland sea. There, burial began its slow work. When researchers later invited Kevin Peterson to join the scientific team describing the new species, he declined with characteristic modesty, explaining that acknowledgement was enough. The scientists chose to honor him regardless. His name became permanently attached to the sea phantom he had discovered. Today, Haliskia stands apart from the other named Australian members of its family. Most are known largely from fragments. Haliskia offers something rarer, a glimpse of the complete animal, suspended once more between ancient sky and ancient sea. Beyond the shoreline, where waves surrendered to mudflats and river mouths, the world changed once again. The Eromanga Sea occupied the center of a vast living landscape, but its waters formed only one part of a much larger system. Around its margins rose scattered islands, remnants of the Australian continent that remained above sea level while marine waters flooded the surrounding lowlands. These islands were green. Across elevated ground stretched extensive conifer forests, their tall trunks supporting layered canopies that filtered sunlight into shifting patterns across the forest floor. Beneath them grew dense communities of ferns and cycads, descendants of plant lineages that had already survived immense spans of geological time. In the warmer northern regions, another botanical experiment was beginning. The earliest flowering plants had started to appear, still uncommon, still sharing the landscape with older forms that had dominated for millions of years. Rainfall, feeding these forests, eventually gathered into streams and rivers. The waterways wound through valleys and lowlands before draining toward the inland sea. Along their journeys, they carried enormous quantities of sediment, eroded from hillsides and deposited where fresh water met marine water. Layer by layer, these sediments accumulated within broad fan-shaped deltas. Those deposits would later become part of the Lower Winton Formation, a geological archive of extraordinary importance. Long after the sea vanished, these rocks would preserve one of the richest dinosaur fossil records in Australia. At the time, however, they were simply part of a living landscape. Moving through the vegetation was Kronosaurus eversi, a small armored herbivore roughly comparable in size to a large dog. Its body carried protective bony plates, transforming an otherwise vulnerable plant eater into a remarkably well-defended animal. The species was discovered near Richmond after its fossil remains were found by a cattle station owner working the land. Across the ancient islands, creatures like Kronosaurus browsed among low-growing plants, while larger herbivores traveled through the forests beyond. Among those larger animals was Muttaburrasaurus. Taller, heavier, and more conspicuous than its armored neighbor, it occupied a different role within the ecosystem. Together, these herbivores converted plant growth into living biomass, supporting food webs that extended across the islands just as surely as marine food webs extended through the sea. The rivers themselves hosted another caste of inhabitants. Within channels, oxbow lakes, and freshwater margins lived Isisfordia duncani, one of the earliest known members of the broader lineage leading toward modern crocodilians. Compared with many later crocodiles, it was relatively small and agile, adapted to a landscape where maneuverability often mattered as much as size. These waterways formed natural corridors linking inland environments to the coast. Sharing those habitats were animals whose ancestry stretched even farther into the past. Temnospondyls, giant amphibians, descended from ancient lineages that originated long before the age of dinosaurs, still survived in these freshwater systems. They were living relics from a world dating back to the Permian period, more than 200 million years earlier. For countless generations, they had occupied rivers, ponds, and wetlands. Yet evolutionary competition was beginning to shift. As early crocodilian relatives diversified, the ecological space available to these amphibians gradually narrowed. Above forests and rivers, another layer of life occupied the sky. Small birds, known as enantiornithines, moved among branches and open air. During the Cretaceous period, this group represented the dominant bird lineage on Earth. One species, Nenantius eos, has been discovered in rocks of Eromanga age near Richmond. These birds were small, agile flyers, filling ecological roles very different from those of the larger pterosaurs that hunted above coastal waters. The contrast was striking. Tiny feathered birds darted through forest canopies, while broad-winged pterosaurs traveled immense distances over sea and shoreline. They shared the same skies, without directly competing for the same resources. Taken together, these islands reveal a broader truth about the Eromanga Sea. It was never merely a marine ecosystem. The sea, forests, rivers, wetlands, islands, and skies formed a single interconnected world. Sediment carried from mountain slopes nourished coastal habitats. Rivers linked inland life to marine environments. Flying animals crossed boundaries that water and land could not contain. Every part influenced every other, all shaped by the same continental transformation unfolding across ancient Australia. The shoreline never stayed where it was. Across human timescales, a coastline can appear permanent, fixed against the horizon and unchanged from one generation to the next. The Eromanga Sea followed a different rhythm. Its boundaries wandered across the continent with extraordinary patience, advancing and retreating over spans so vast that entire ecosystems appeared and vanished between each movement. The sea breathed, not in years or centuries, but in geological pulses. Over approximately 20 million years, the Eromanga Basin experienced at least 4 major cycles of flooding and retreat. Each advance of marine water, known as a transgression, left its signature in sediment. Each withdrawal, known as a regression, created another distinct layer, stacked one above another. These deposits record the history of the sea, much as growth rings preserve the history of a tree. The first great flooding began during the Barremian and Aptian ages, between roughly 125 million and 113 million years ago. Seawater entered the basin from more than one direction. To the north, marine waters spread through the Carpentarian Basin. To the east, another connection formed through the Surat Basin. Together, these gateways allowed the ocean to pour into the low-lying interior of the continent. The transformation unfolded gradually. Valleys disappeared beneath rising water. Plains became shallow marine shelves. Former river systems were absorbed into expanding embayments. Habitats that had once supported terrestrial communities found themselves incorporated into an inland sea. During the Aptian interval, between approximately 120 million and 113 million years ago, the flooding reached an especially remarkable stage. Geological evidence suggests that temporary marine connections may have extended entirely across the continent. For a relatively brief interval in Earth's history, waters of the Eromanga Basin may have linked with the Carnarvon Basin on the western coast. If that interpretation is correct, Australia experienced a striking moment of division. The continent may have existed as two large landmasses separated by a continuous east-to-west seaway. What appears solid and indivisible on modern maps became fragmented by the slow expansion of shallow marine waters. Yet the sea never remained at maximum extent for long. Retreat eventually followed advance. A renewed transgression arrived during the early and middle Albian age, between approximately 110 million and 105 million years ago. This flooding produced the greatest extent of the Eromanga Sea, the phase that formed the backdrop for the marine world explored throughout the previous sections. At this moment, the basin contained its richest ecosystems, its largest predators, and its broadest network of connected habitats. Each cycle reshaped far more than geography. When marine waters advanced, forests, floodplains, and terrestrial habitats disappeared beneath the sea. When the waters retreated, marine environments contracted and fragmented. Coastal marshes emerged where open water had once existed. New ecological opportunities appeared while older ones vanished. Along retreating shorelines, extensive swamps developed. Plant material accumulated within waterlogged environments where decomposition remained incomplete. Layer after layer of organic debris gathered across these wetlands. Later flooding episodes buried the material beneath fresh sediments, preserving it deep underground. Over immense spans of time, some of these deposits would become coal. The connections linking the sea to the wider ocean also changed. During an early Albian regression, the eastern seaway through the Surat Basin closed. From that point onward, the Eromanga Sea relied primarily upon its northern connection to maintain contact with the global ocean. The basin became increasingly isolated, and its internal conditions grew more sensitive to external changes. Its vulnerability stemmed from its shape. The Eromanga Sea was broad but shallow. Its entrances were relatively narrow. Because of this geometry, even modest fluctuations in global sea level could produce dramatic consequences. A drop of only a few tens of meters could expose vast stretches of seafloor and shift coastlines by hundreds of kilometers, which is about 124 miles. What required millions of years to assemble could begin withdrawing surprisingly quickly. The great inland sea expanded, contracted, advanced, and retreated in recurring pulses, each movement leaving another layer in the rocks, another chapter in the long breathing cycle of a vanished world. The end began so gradually that no creature living within the Eromanga Sea could have recognized it as an ending. There was no single season when the waters suddenly vanished. No wall of destruction crossed the basin. No moment when the ecosystem stopped and another immediately took its place. Instead, the transformation unfolded across spans of time so immense that countless generations lived and died while the process continued, almost unnoticed. By approximately 100 million years ago, during the late Albian Age, the final regression had begun. Unlike earlier cycles, this retreat would not reverse. Two forces worked together to reshape the continent. The first was a decline in global sea levels. As ocean levels fell around the world, the shallow connections feeding the Eromanga Sea became increasingly vulnerable. Water that had once flowed freely into the basin found its pathways narrowing. Coastlines advanced outward. Areas that had remained submerged for millions of years gradually emerged into open air. The second force came from beneath the continent itself. Australia was beginning a long geological separation from Antarctica. The process would become increasingly significant around 85 million years ago, altering the structure of the crust over vast distances. As tectonic forces slowly reorganized the southern continents, portions of the Australian interior experienced uplift. The basin tilted almost imperceptibly. Land rose where water had previously collected. Neither process was dramatic on a human scale. Together, however, they proved relentless. The rocks preserve a detailed record of this transition. Near the end of the marine chapter lies the Mukunda Formation, representing some of the final sediments deposited while seawater still occupied the basin. Above it appears a fundamentally different world. The Winton Formation records river systems, floodplains, freshwater channels, and terrestrial environments. The sequence captures the replacement of one ecosystem by another. a marine realm became a continental landscape. The retreat did not occur evenly across the basin. Shallow regions disappeared first, exposing broad expanses of former seafloor. Deeper channels persisted longer, forming isolated marine refuges disconnected from the larger body of water that had once surrounded them. Within these remnants, conditions deteriorated. As circulation weakened, oxygen levels declined further. Salinity increased as evaporation concentrated dissolved minerals. Water exchange with the open ocean became increasingly limited. Habitats that had supported thriving communities for millions of years contracted into shrinking pockets. The coastline migrated steadily. Locations that had once overlooked open water found themselves far inland. River systems extended across newly exposed ground. Wetlands formed where bays had existed. Sediments accumulated across former marine shelves. For the great reptiles of the sea, the consequences were profound. Many of these animals had evolved within the inland basin itself. Their lives were tied to its geography, its food webs, and its connections to the ocean. As those connections weakened and disappeared, opportunities for dispersal became increasingly restricted. The marine environment that sustained them simply occupied less and less space. Generation after generation encountered a smaller world. The contraction continued until marine habitats fragmented beyond recovery. Eventually, the remaining pools vanished as well, leaving behind only sediments, minerals, and fossils buried beneath the surface. What makes this story especially striking is its timing. The famous asteroid impact that marked the end of the Cretaceous period and contributed to the extinction of the non-avian dinosaurs occurred approximately 66 million years ago. By that time, the Eromanga Sea had already vanished for at least 34 million years. Its disappearance had nothing to do with that catastrophe. No asteroid ended this sea. No sudden extinction event erased it. No singular disaster closed the chapter. Instead, the Eromanga Sea experienced a fate far more gradual. Water withdrew from the continent little by little. Coastlines shifted, connections closed, habitats shrank. Marine sediments gave way to river deposits. The pulse that had carried the sea through repeated advances and retreats finally ceased. In the end, the disappearance of one of Earth's greatest inland seas was not marked by violence, but by persistence. Geological forces worked patiently across millions of years until the basin that had once held marine reptiles, ammonites, sharks, pterosaurs, and vast drifting swarms contained only rivers, floodplains, and the memory of water preserved within stone. Long after the last marine reptile disappeared, and long after the final shoreline faded from the continent, the Eromanga Sea continued shaping Australia from beneath the ground. Its waters vanished, but its architecture remained. Every flooding event, every retreat, every shift in coastline left a physical trace within the basin. Over millions of years, sediments accumulated layer upon layer across the former seafloor. Sands arrived from distant river systems. Fine silts settled through deeper water. Mud collected during calmer intervals. Volcanic material drifted into the basin from landscapes far beyond the horizon. Time compressed these deposits. Pressure increased. Water was expelled. Loose sediment gradually hardened into stone. What had once been soft layers on the floor of an inland sea became an immense stack of geological records extending across a significant portion of the continent. Yet the resulting rock sequence was not uniform. Some layers became sandstone, composed of grains packed together while still preserving countless microscopic pathways between them. Water could move through these rocks, slowly, often imperceptibly, but it could move. Other layers became mudstone and siltstone. Their particles were far finer and more tightly packed. Water struggled to pass through them. These rocks acted as barriers, restricting movement and trapping fluids beneath or between them. Repeated flooding and retreat created an alternating arrangement of these materials. Permeable sandstone layers formed natural conduits. Impermeable mudstone and siltstone layers formed seals above and below them. Together, they created something extraordinary. The vanished sea unintentionally built one of the largest groundwater systems on Earth. This structure is known today as the Great Artesian Basin, covering more than 1,700,000 square kilometers, which is about 656,000 square miles. It extends roughly 2,400 kilometers, which is about 1,491 miles, from Cape York in Queensland to Dubbo in New South Wales. Beneath vast regions of eastern and central Australia lies a hidden network of water-bearing rocks whose origins can be traced directly to the ancient cycles of the Eromanga Basin. The process sustaining this system begins far from the arid interior. Rain falling along the Great Dividing Range enters exposed sandstone formations at the eastern margins of the basin. There, water seeps downward into porous rock and begins an extraordinarily slow journey. Unlike rivers flowing across the landscape, groundwater travels through countless tiny spaces between mineral grains. The movement is measured not in kilometers each day, but sometimes in only a few meters each year. A drop of rain entering the system today may continue traveling long after modern civilizations have changed beyond recognition. Some water currently stored within the basin has remained underground for more than 1 million years. In many cases, water entering recharge zones requires hundreds of thousands of years to emerge again in distant regions of the basin. The quantity involved is astonishing. Estimates suggest that approximately 64,900 million megaliters of water are stored within the Great Artesian Basin. It is the largest groundwater basin in Australia and among the largest known anywhere in the world. Yet storage alone does not explain its most remarkable behavior. Because the intake regions occur at higher elevations along the eastern margins, water entering the system possesses gravitational potential. As additional water accumulates behind it, pressure develops within confined sandstone layers trapped beneath impermeable seals. This pressure can become immense. In certain locations, when a pathway to the surface exists, the water rises naturally without pumps or mechanical assistance. The force comes entirely from the weight of water stored higher within the basin. This phenomenon is known as artesian pressure. What makes these locations so remarkable is that they transform buried geological history into something visible. Water that began its journey through rocks formed by an ancient inland sea can emerge naturally at the surface after traveling underground for immense spans of time. The sea itself disappeared millions of years ago, yet the structures it built continue directing the movement of water beneath Australia, carrying the legacy of a vanished ocean through stone, pressure, and time. A fossil normally preserves the shape of a lost organism. Bone becomes stone, details soften, and the remains settle into the geological record as mineralized echoes of once living creatures. The Eromanga Sea sometimes followed a far stranger path. Deep beneath sediments laid down by vanished waters, chemistry began performing a transformation so unusual that it would eventually produce some of the most extraordinary fossils on Earth. This is where the story of the gemstone bones returns, and where one of the oldest threads running through this journey finally finds its answer. The conditions were exceptionally rare. Cold marine environments covered much of the basin. Oxygen was often scarce beneath the surface sediments. Iron-rich deposits accumulated across broad regions of the seafloor. Volcanic material contributed abundant silica to the system. Burial occurred within settings where decay slowed and preservation became possible. Together, these factors created an environment capable of producing opalized fossils on a scale found almost nowhere else in the world. Opal itself is composed primarily of hydrated silicon dioxide. Unlike many familiar minerals, it does not form through the orderly crystal structures seen in quartz. Instead, it begins as silica-rich water carrying dissolved material through rock and sediment. When conditions change, the dissolved silica is deposited and gradually solidifies. The process begins with death. A fish, an ammonite, a marine reptile, or any other organism settles into sediment and becomes buried. Over immense spans of time, the organic components of the skeleton slowly decay. Minerals within the original bone may dissolve as groundwater continues moving through surrounding layers. Eventually, the original material can disappear almost entirely. What remains is not the bone itself, but a perfect three-dimensional mold left behind within the surrounding rock. Every ridge, cavity, channel, and microscopic detail survives as an empty space, preserving the exact form of the original structure. That empty space becomes the stage for a second act. Groundwater enriched with dissolved silica moves through the sediment. Slowly, almost unimaginably slowly, it enters the mold. The cavity begins filling with silica gel carried by the water. The timescale stretches across millions of years. As water gradually leaves the system, the silica remains behind. Within the growing deposit, microscopic spheres arrange themselves into remarkably regular patterns. Their organization becomes so precise that they interact with visible light in a unique way. When light enters the opal, different wavelengths are separated and redirected. The result is the shifting display of color that precious opal is famous for. Flashes of red, blue, green, violet, and gold appearing to move beneath the surface as viewing angles change. No pigment creates these colors. They emerge entirely from structure. This is why opalized fossils are so remarkable. The fossil is not stained by gemstone. It is not coated by gemstone. The original material has been replaced, detail by detail, with gemstone itself. In some specimens, the replacement is so accurate that internal structures become visible in ways impossible with ordinary fossils. Because opal can be translucent, researchers are sometimes able to observe features hidden within the specimen rather than only examining its exterior surface. Few places illustrate this phenomenon more dramatically than Lightning Ridge in New South Wales. It remains the only known location producing black opal fossils. Dinosaur bones, jaws of ancient mammals, marine invertebrates, and even microscopic organisms have all been preserved through this extraordinary process. The Australian Opal Centre houses more than 4,000 opalized fossils, the largest collection of its kind anywhere in the world. Many specimens have yet to receive detailed scientific description, meaning their stories remain partially hidden within their luminous interiors. None of this would have been possible without the ancient sea. The Eromanga Basin supplied the sediments, the chemistry, the groundwater pathways, and the burial conditions. The sea created the opportunity. Time supplied the patience. Then, in the year 1987, deep beneath Coober Pedy, a miner broke into an underground passage and discovered something that seemed impossible. A fossil transformed completely into gemstone. The story begins not in a museum, a laboratory, or a fossil quarry, but beneath the earth, inside a maze of tunnels carved through opal-bearing rock in South Australia. In the year 1987, an opal miner working beneath Coober Pedy broke into a fresh section of stone. The walls around him glittered faintly in the artificial light. Such discoveries were common in a region famous for gemstones, yet what emerged from the rock that day belonged to an entirely different category of treasure. Embedded within the wall was a skeleton. Not a skeleton preserved as ordinary fossilized bone, but one transformed into opal. Vertebrae shimmered with shifting colors. Fragments of ribs flashed green, blue, red, and gold. The remains seemed suspended between biology and mineral, between an animal and a gemstone. Recognizing value but not fully understanding what had been uncovered, the miner attempted to extract the specimen himself. The task was extraordinarily delicate. Fossils replaced by opal can be beautiful, yet they are often fragile. Mining tools designed for removing rock are poorly suited to preserving intricate anatomy. Several pieces were damaged during the effort. Even so, enough survived to reveal that the discovery was exceptional. The fossil eventually came into the possession of an Australian businessman named Sid Londonish, who recognized that the specimen deserved closer examination. To make sense of the fractured collection of opalized bones, he enlisted archaeologist Paul Willis. What arrived before Willis resembled an enormous three-dimensional puzzle. Fragment by fragment, he worked to reconstruct the animal. Bones were compared, matched, and carefully assembled. As the shape emerged, the fossil gradually revealed itself as one of the most extraordinary specimens ever recovered from the ancient inland sea. Along the way, Willis gave the animal a nickname. He called it Eric, borrowing the name from the Monty Python song about Eric the half-a-bee. The joke was casual and temporary, yet it endured. Decades later, the fossil remains known to millions simply as Eric. The reconstruction produced another surprise. Within the rib cage lay a cluster of smooth, rounded stones. These were gastroliths, the stomach stones swallowed by many plesiosaurs. Their exact function remains debated, though they may have assisted with buoyancy control, digestion, or both. Nestled among those stones was something even more remarkable. There, preserved within Eric's body cavity, were the opalized vertebrae of a small fish. More than 115 million years after the meal had been eaten, traces of it remained inside the predator that consumed it. Willis gave the fish a name as well. She became Wanda. Together, Eric and Wanda formed a snapshot of a vanished ecosystem, preserved not merely as fossils but as gemstones. Scientific study eventually identified Eric as Eromangasaurus demacillus, a relatively small pliosaur from the Eromanga Sea. Unlike the giant apex predators that dominated open waters, this animal measured about 2.5 meters in length, which is about 8.2 miles. His skeleton was more than 90% complete and contained roughly 36 kilograms of precious opal. Yet, Eric's future soon became uncertain. Financial difficulties forced Londonish to consider selling the specimen. Interest arrived from buyers around the world. Many saw Eric not as a scientific treasure, but as a source of valuable gemstones. The opal contained within the skeleton alone possessed considerable monetary value. For a time, the possibility became alarmingly real that the fossil could be dismantled, vertebrae might become jewelry, ribs could be cut apart and polished. One of the most complete opalized skeletons ever discovered risked disappearing forever into private collections and decorative objects. A public campaign emerged in response. The Australian science television program Quantum launched an effort known as Save Eric. Schoolchildren organized fundraisers, businesses contributed support, donations arrived from people who believed the fossil belonged to history rather than commerce. More than $450,000 was eventually raised. In the year 1993, the Australian Museum acquired Eric, ensuring his preservation for future generations. Today, he rests within a protected display in Sydney. His opalized bones still shimmer beneath museum lights. Wanda remains inside his ribcage, exactly where she came to rest more than 115 million years ago, carried across unimaginable spans of time by stone, chemistry, and chance. Some places seem defined by their distance from the sea. Eromanga is one of them. Today, this small settlement sits deep within the Australian interior, surrounded by broad horizons, dry country, oil fields, and opal-bearing ground. According to the census conducted in the year 2021, only 98 people call it home. The population is smaller than that of many city buildings, yet the landscape surrounding it contains one of the richest geological archives on the continent. The name Eromanga is believed to come from an Aboriginal expression often interpreted as hot windy plain or hot gale plain. The precise linguistic origin remains uncertain. Many of the communities whose languages once named these places endured profound disruption before detailed records could be preserved. Like so much of Australia's deeper history, fragments remain while complete stories have been lost. The modern town appears far removed from any coastline. Indeed, it is frequently described as one of the most landlocked settlements in Australia. The claim is sometimes debated by geographers, yet it captures an essential truth about the place. Standing beneath its vast sky, surrounded by red earth stretching toward distant horizons, the ocean feels impossibly far away. Yet the ground beneath every building tells a different story. Beneath the roads, beneath the houses, beneath the dust carried by inland winds, lies the record of an ancient marine world. If a drill were lowered beneath the town and a continuous core extracted from the underlying rock, layer after layer would reveal evidence of the vanished inland sea. Marine sediments would emerge from the depths. Fossil shells would appear. Chemical signatures left by ancient saltwater would remain preserved within minerals deposited more than 100 million years ago. The sea disappeared, but its memory remained embedded in stone. That memory now shapes much of the town's identity. Travelers arrive not because of modern industry, but because Eromanga occupies a unique place in Australia's paleontological landscape. Fossils continue to emerge from surrounding properties, often discovered not by professional researchers but by the people who live and work in the region. The pattern has repeated itself many times. A station owner notices an unusual shape protruding from the ground. A fragment of bone appears after rainfall. A curious object emerges during routine work. What begins as an ordinary day can become the beginning of a scientific discovery. Among the most remarkable finds is Australodonton cooperensis, a giant titanosaur known by the nickname Cooper. This immense herbivore is estimated to have weighed between 30 and 40 tons and reached approximately 25 to 30 meters in length, which is about 15.5 to 18.6 miles. Its remains were discovered on a nearby cattle station, transforming understanding of the giant dinosaurs that once inhabited this region after the sea withdrew. The Eromanga Natural History Museum was established to house and study discoveries such as these. For a town of fewer than 100 residents, it has become an extraordinary destination, drawing visitors, researchers, and fossil enthusiasts from across Australia and beyond. Yet even the gemstones beneath the region carry echoes of the ancient ocean. The opal fields surrounding Eromanga exist because of geological processes rooted in the history of the Eromanga Sea. The chemistry of the sediments, the movement of groundwater, and the slow replacement of fossil material with silica all trace their origins to environments established long ago beneath marine waters. Every opal extracted from the surrounding country represents another expression of that inheritance. What makes Eromanga remarkable is not merely that it sits where a sea once existed. Many places occupy former coastlines or ancient seabeds. Eromanga rests directly upon the remains of an entire vanished world, one whose predators, reptiles, ammonites, and drifting plankton disappeared millions of years before humanity arrived. Today, 98 people live upon that ancient seafloor. Around them stretch rocks filled with fossils, gemstones born from long-vanished chemistry, and sediments deposited beneath waters that disappeared before the final age of dinosaurs had even come to an end. The ocean is gone, yet its presence remains woven through every layer beneath the town. Before Kronosaurus became a museum giant, before its skull appeared in scientific illustrations and documentary reconstructions, it existed as scattered bones, weathering slowly from the earth beneath an immense Queensland sky. The discovery began in the year 1926 at Army Downs Station near Richmond. A station worker named Ralph Thomas noticed unusually large bones emerging from surface rock. Fossils were not unknown in this region, yet these remains belonged to something far larger than the ordinary fragments occasionally revealed by erosion. Piece by piece, the skeleton emerged from the stone. This was not merely an isolated tooth or a section of jaw. The deposit contained a substantial portion of a single animal, including elements of the skull, vertebrae from the backbone, portions of the shoulder and hip girdles, and major limb bones. Together, they represented one of the most important marine reptile discoveries ever made in Australia. News of the find eventually traveled far beyond Queensland. At that time, many of the world's largest natural history institutions were actively seeking spectacular fossils. Ancient Australia remained comparatively unexplored from a paleontological perspective, and the possibility of recovering a giant marine predator from the interior of the continent attracted considerable attention. In the year 1932, an expedition from Harvard University arrived in Outback, Queensland. The team was led by William Ellery Cheval and traveled across a landscape that seemed almost impossibly distant from the ocean that had once existed there. The excavation was challenging. Fossils embedded within hard rock required careful removal, stabilization, and transport. Yet the effort succeeded. The specimen was recovered, packed, and shipped across the Pacific Ocean to the Museum of Comparative Zoology in Cambridge, Massachusetts. There it entered a new chapter of its history. Researchers prepared the bones, studied their anatomy, and eventually mounted the skeleton for public display. Visitors could now stand beneath one of the largest marine predators ever discovered from the ancient inland sea. For many people, this specimen became the image of Kronosaurus itself. Yet a curious problem emerged during reconstruction. No complete skeleton existed for comparison. Paleontologists were working with incomplete information, attempting to rebuild an animal that had vanished more than 100 million years earlier. To create a mounted display, assumptions had to be made regarding missing portions of the backbone. Some of those assumptions proved incorrect. Additional vertebrae were included in the reconstruction, making the mounted animal significantly longer than it should have been. The resulting display suggested a creature approaching 13 meters in length, which is about 8.1 miles. That estimate entered scientific discussions, museum labels, books, and popular culture. For decades, the oversized reconstruction influenced perceptions of Kronosaurus. Only later did more detailed study demonstrate that the true length was likely closer to 9 to 10 meters, which is about 5.6 to 6.2 miles. Even at the corrected size, Kronosaurus remained an immense predator, yet the revision revealed how strongly a single specimen can shape understanding when evidence is limited. Meanwhile, additional discoveries continued across Queensland. Fossils attributed to Kronosaurus were recovered from Richmond, Hughenden, Julia Creek, Boulia, and surrounding regions. Each new specimen added information about anatomy, growth, variation, and distribution. Collections expanded within Australian institutions, allowing researchers to compare material from multiple sites rather than relying upon a single famous skeleton. Today, important remains are housed in places such as Kronosaurus Corner, the Queensland Museum, and other Australian collections. Yet the most celebrated specimen remains at Harvard, where it has spent nearly a century. There is a certain irony in that journey. The animal lived within Australian waters. It hunted Australian marine reptiles. It died on an Australian seafloor. Yet, its most famous skeleton crossed an ocean after discovery and became part of another nation's scientific heritage. Back in Richmond, the story continues to grow. Kronosaurus Corner now houses more than 1,150 unique fossil specimens from the Eromanga Sea, including the remarkable Richmond polycotylid, among the most complete vertebrate fossils ever discovered. In the year 2019, a traveling gemstone hunter searching the museum's public dig site uncovered a pearl approximately 100 million years old, among the oldest ever documented. Even now, the ancient sea continues surrendering fragments of its memory, one discovery at a time. A boat seems like an odd thing to carry into a desert. Yet, in the year 1844, that is exactly what the explorer Charles Sturt did. As he departed Adelaide and pushed toward the vast interior of Australia, he brought with him a vessel intended for water that he was convinced existed somewhere beyond the horizon. The belief was not unreasonable for its time. Across the continent, rumors persisted of a great inland sea hidden within the unexplored center. Rivers appeared to flow toward low-lying basins. Vast salt lakes occupied depressions across the landscape. Flat country stretched for immense distances. To many observers, these features suggested the existence of a substantial body of water waiting to be discovered. Sturt accepted the possibility wholeheartedly. His expedition pressed deeper into some of the harshest country on Earth. Dry channels twisted through the landscape. Ancient lake beds reflected sunlight from pale crusts of salt. Horizons shimmered beneath relentless heat. Again and again, the terrain seemed to hint that larger waters might lie ahead. They never appeared. Instead, the expedition encountered hardship of a different kind. Temperatures climbed to extraordinary levels. The party became stranded for months beside a remote waterhole, unable to continue safely. Conditions grew so severe that several members came close to death. Historical accounts describe temperatures exceeding 50 degrees Celsius or 122 degrees Fahrenheit. Yet, even after enduring such conditions, Sturt did not abandon his conviction entirely. He returned believing that an inland sea still existed and that he had simply failed to locate it. He was not alone. Other explorers reached similar conclusions while traversing the Australian interior. John Oxley, Thomas Mitchell, and Edward John Eyre all recorded observations that seemed difficult to explain. They encountered immense flat basins. They crossed ancient lake systems. Most intriguingly of all, they discovered marine shells embedded within rocks, far from any coastline. To 19th century observers, such evidence appeared compelling. If shells existed in the interior, perhaps seawater had once occupied the region. If broad basins stretched across the landscape, perhaps remnants of that sea still survived somewhere beyond the next ridge or horizon. In a curious way, they were correct. A sea had indeed occupied the heart of the continent. What they misunderstood was time. The shells emerging from weathered rock were not recent remains. They were not evidence of a vanished lake from a few centuries earlier. They belonged to creatures that had lived during the age of dinosaurs. Ammonites, bivalves, and fragments of belemnites had rested within those rocks for more than 100 million years before the explorers arrived. Erosion had merely brought them back to the surface. The landscape itself was offering clues, but the clues described a world far older than anyone then imagined. By the time Sturt carried his boat into the interior, the Eromanga Sea had already been gone for approximately 95 million years. The coastlines had vanished. The marine reptiles had disappeared. Rivers and floodplains had replaced the seafloor. Entire mountain ranges had risen and worn away. Yet, traces of the sea remained everywhere beneath their feet. The irony becomes even deeper when viewed through the lens of modern geology. The explorers searched desperately for water. Their journals repeatedly describe thirst, uncertainty, and the struggle to locate reliable supplies. Expeditions were planned around scarce waterholes. Progress depended upon finding sources that might sustain both people and animals. Unknown to them, an immense reserve of water already existed below the landscape. In many regions, the groundwater system created by the ancient Eromanga Basin lay approximately 200 meters beneath the surface, which is about 656 feet. The very sea they sought had helped construct the geological architecture that stored this hidden resource. Had they possessed the technology to reach it, artesian water could have risen from depths below their camps. Instead, they crossed the country above it, reading fragments of the story without access to its conclusion. The shells were real. The ancient seafloor was real. The evidence was all around them. They stood upon the answer, surrounded by remnants of a vanished ocean, while searching for a sea that had disappeared tens of millions of years before their journey began. Not every trace of the ancient sea lies buried beneath stone. In certain places, the story rises back to the surface. Across the interior of South Australia and Queensland, water emerges from the earth in locations that seem almost impossible. Vast stretches of arid country extend toward distant horizons. Salt flats shimmer beneath the sun. Vegetation becomes sparse. Yet, amid this demanding landscape, pools of fresh water appear, fed not by rainfall or rivers, but by geological forces operating deep underground. These are the mound springs. Some form low domes of mineral-rich sediment. Others emerge as clusters of pools, surrounded by reeds and green growth. From a distance, they can appear like small islands scattered across a sea of desert, places where life gathers around a source that has persisted through immense spans of time. The water reaching these springs has undertaken an extraordinary journey. Rain falling along the eastern margins of the Great Artesian Basin enters exposed sandstone layers and begins moving through the subsurface. The process is remarkably slow. In some regions, water advances only a few meters each year. Decades pass. Centuries pass. Sometimes thousands of years pass. Eventually, geological conditions force portions of that water upward. Pressure accumulated within confined sandstone layers, pushes against weaknesses in the overlying rocks. Where pathways exist, water rises naturally to the surface without pumping or mechanical assistance. The result is a spring fed by groundwater whose journey began long before modern history. Across the basin, there are approximately 6,300 individual springs. Roughly 80% occur within South Australia, where some of the most extensive spring complexes persist today. Their significance becomes clearer when viewed against the surrounding environment. Australia is the driest inhabited continent on Earth. Within some regions of the interior, permanent freshwater sources are exceptionally rare. For immense distances, water may be absent from the landscape altogether, yet these springs continue flowing, sustaining life where little else can. Around them, biological communities developed in isolation. Researchers have documented nearly 500 species associated with Great Artesian Basin spring ecosystems. Many are small invertebrates found nowhere else on the planet. Over millions of years, populations became separated from one another by surrounding desert. A species inhabiting one spring group could be effectively isolated from relatives living only a short distance away. Each spring complex became its own evolutionary island. Life adapted to local conditions, producing unique forms that survived because the springs endured. The surrounding landscape acted as a barrier, preventing easy movement between populations and allowing distinct evolutionary pathways to unfold. Long before scientific study recognized their importance, these waters already held profound significance for people. Aboriginal and Torres Strait Islander communities relied upon the springs for survival across countless generations. Archaeological evidence indicates continuous human use extending back at least 40,000 years and possibly as much as 65,000 years. Stone tools, hearth remains, and other traces of occupation reveal enduring relationships between people and these precious sources of fresh water. Among the traditional custodians most closely connected with the spring country are the Eromangasaurus people, whose ancestral lands encompass many of the major spring systems in South Australia. Today, they help manage approximately 69,000 square kilometers of country, which is about 26,641 square miles, including some of the most significant spring complexes within the basin. The springs also occupy an important place within cultural traditions and Dreamtime narratives. They are woven into stories, responsibilities, and systems of knowledge that connect people to landscape across deep time. What makes these places especially remarkable is the continuity they represent. Water entering the aquifer today may not emerge for centuries or longer. The sandstone through which it travels was deposited when the Eromanga Sea covered the continent's interior. The pathways guiding its movement were established by geological processes set in motion more than 100 million years ago. Each spring, therefore, links distant ages together. The water rising into the desert is modern water, yet it moves through structures created by an ancient sea. The same event that flooded the heart of Australia during the age of marine reptiles continues, even now, to provide fresh water in one of the most demanding environments on Earth. A drop of water falling on a mountainside today may begin a journey longer than the rise and fall of entire civilizations. It seeps into exposed sandstone along the eastern margins of the Great Artesian Basin and disappears from view. Gravity draws it downward. Pressure guides it onward. Year after year, century after century, it moves through narrow spaces between mineral grains, advancing so gradually that a human lifetime is almost meaningless beside its pace. Far to the west, another drop finally emerges from a spring after spending ages underground. The two waters belong to the same system, yet they are separated by spans of time so vast that neither shares the same world. The Great Artesian Basin contains an estimated 64,900 million megaliters of groundwater. Hidden beneath much of inland Australia, it forms one of the largest groundwater reserves on Earth. Some of the water moving through its deepest pathways has remained underground for more than 1 million years. Water entering recharge zones in the highlands today may not reach springs near the basin's western margins for hundreds of thousands of years. It is difficult to think of water as ancient. Rivers feel immediate. Rain belongs to the present moment. Lakes rise and fall with the seasons. Yet beneath the continent exists a reserve that operates according to geological rhythms, moving through structures created in a world inhabited by marine reptiles and drifting continents. Modern Australia depends upon this inheritance more than many people realize. Across Queensland, New South Wales, South Australia, and the Northern Territory, communities draw upon basin water for daily life. Pastoral stations rely upon it. Agricultural operations depend upon it. Mining developments use it. Towns scattered across the interior receive drinking water from it. Economic activity, supported by the basin, is estimated at approximately $12.8 billion each year. Beneath that figure lies a simpler reality. Without this groundwater, much of inland Australia could support only sparse human occupation. Settlements that now appear permanent would struggle to endure. Yet every ancient reserve carries limits. For more than a century, wells have been drilled into the aquifer. Many early boreholes flowed continuously once pressure was released. Water spread across the landscape, filling channels and evaporating beneath the sun. At the time, the supply seemed inexhaustible. The hidden reservoir appeared so immense that few imagined it could be diminished. Gradually, the consequences became visible. As pressure declined across parts of the system, natural spring flows weakened. Water that had risen unaided for countless generations no longer reached the surface with the same force. Some springs shrank. Others ceased flowing altogether. The effects extended beyond hydrology into ecology and culture, touching species and communities that depended upon those waters. Industrial extraction added further demands. The Olympic Dam mining operation in South Australia draws tens of millions of liters from groundwater sources each day. Supporters view such extraction as an important contributor to economic development. Critics argue that long-term environmental consequences require greater caution, particularly when dealing with a resource that renews so slowly. In response, extensive bore capping and piping programs have reduced waste across large portions of the basin. Water once lost to evaporation is increasingly directed where it is needed. These efforts have helped stabilize pressure in some regions, though the balance between conservation and extraction remains an ongoing challenge. What makes the discussion unique is the nature of the resource itself. Many water supplies replenish within years or decades. The Great Artesian Basin does not operate on human timescales. Much of its stored water accumulated through processes measured in thousands and millions of years. Once removed, replacement occurs so slowly that for practical purposes, the loss is permanent. And so the story circles back to its beginning. The ancient sea vanished long before human beings arrived on the continent. Its coastlines disappeared. Its creatures became fossils. Its waters withdrew from the surface world. Yet the architecture it created endured beneath the ground, layer upon layer of sandstone and stone seals, preserving a hidden reservoir. The sea itself is gone. Its memory still flows. The basin is still there, beneath the towns, the grazing lands, the mining districts, and the broad interior plains lies the same Great Depression that once held an inland sea. The water is gone, the coastlines erased, yet the underlying shape remains written into the continent. Rock remembers long after oceans depart. Perhaps that is why geologists are occasionally asked a surprising question. Could the Eromanga Sea return? The question may sound like the beginning of a work of fiction, yet scientists do not dismiss it outright. They understand that the forces responsible for creating the ancient sea were not unique events occurring only once in Earth's history. They were the product of geological circumstances that have appeared repeatedly across different continents and different eras. The first ingredient was subsidence, the gradual sinking of sections of Earth's crust. As the interior basin deepened, space became available for water to accumulate. The second ingredient was elevated global sea level. When enough water occupied the world's oceans, marine connections could extend far inland through low-lying regions. The third ingredient was geography itself, the particular arrangement of basins, seaways, and continental margins that allowed seawater to enter the heart of Australia. None of these processes has vanished from the planet. The depression associated with the Great Artesian Basin still exists. The ancient structural weakness that helped accommodate the sea has not been completely erased. Even after millions of years of uplift, erosion, and tectonic adjustment, the landscape retains traces of the broad inward slope that once guided marine waters toward the continent's center. The Earth beneath Australia remains part of an unfinished story. For the sea to return, several major changes would need to occur. Global sea levels would have to rise dramatically, far beyond the increases projected within present climate forecasts. Additional crustal subsidence could deepen portions of the basin once again, creating new accommodation space for incoming water. A renewed marine connection from the north might also be required, allowing ocean water to penetrate deep into the interior. These are immense changes. Yet geology specializes in immense changes. Mountain ranges appear and disappear. Ocean basins open and close. Continents split apart and later collide. Processes that seem impossible within a human lifetime become ordinary when measured across millions of years. Some models examining the distant future suggest that continental interiors around the world may experience renewed marine transgressions as planetary conditions evolve. Coastlines migrate, sea levels fluctuate, tectonic forces reshape the surface. Given enough time, landscapes that are dry today may once again lie beneath water. Researchers who have considered the future of the Eromanga region acknowledge that some form of renewed inland sea is theoretically possible. Potential pathways include long-term climate change, major tectonic adjustments, or even the consequences of a large extraterrestrial impact altering global conditions. None of these possibilities belongs to the foreseeable future. Their timescales stretch from hundreds of thousands to many millions of years. Such spans of time are difficult to comprehend. Human history occupies only a thin layer atop the much deeper chronology of the planet. Languages emerge and disappear. Nations form and dissolve. Entire civilizations rise and fall, while continents continue their patient motion beneath them. Whether any human civilization would exist to witness the return of an inland Australian sea is impossible to know. What geology does suggest is something broader. The present shape of Australia is not permanent. Neither are its deserts, rivers, coastlines, or drainage systems. They are temporary arrangements of stone and water preserved for a moment within an ongoing process of transformation. What appears fixed on maps is, in geological terms, already changing. Long before the first marine reptile entered the Eromanga Sea, another landscape occupied this place. Long after the last artesian spring has altered its course, another landscape will follow. The continent has never stopped becoming something else. And beneath the modern interior, the old basin waits, carrying the faint outline of a sea that vanished, yet never completely surrendered the possibility of returning. Sometimes the oldest traces of a vanished world are small enough to fit in the palm of a hand. A person walking across a paddock in western Queensland may notice an unusual shape among the stones. It does not announce itself with grandeur. There are no cliffs carved into dramatic forms, no towering skeleton emerging from the earth, only a weathered rock resting beneath an open sky. Turn it over, and a spiral appears. Within the stone lies the imprint of an ammonite, a marine creature that drifted through the waters of the Eromanga Sea approximately 110 million years ago. Its shell, once carried through cold inland currents, now rests beneath grazing cattle and distant windmills. The fossil is not protected behind glass. It is not illuminated by museum lights. It exists where erosion left it, waiting for someone to notice. This happens more often than many people realize. Across vast regions of Queensland, ancient formations reach the surface. The Winton Formation stretches across broad areas of outback country. The Tullabuck Formation emerges from the landscape in scattered exposures. The Alaru Mudstone appears in places where weather and time have gradually stripped away younger layers above it. Together, these rocks preserve fragments of a lost ecosystem on a remarkable scale. Yet much of this country remains unsurveyed in any comprehensive way. The distances are immense. Properties can extend across areas larger than some nations. Roads are few. Access is difficult. Professional paleontologists, despite decades of work, have examined only a fraction of what lies exposed across the region. As a result, many discoveries arrive through unexpected hands. Cattle station owners uncover bones while repairing fences, moving livestock, or inspecting water infrastructure. Fossil enthusiasts notice unusual shapes protruding from weathered ground. Museum volunteers participate in excavations and reveal specimens that have remained hidden for geological ages. Traveling gemstone hunters occasionally encounter objects that prove to be far more significant than they first appear. Again and again, the story repeats. An observation, a curious shape, a fragment of bone, a stone that seems slightly different from the others nearby. Then an entire chapter of prehistory emerges. The Great Expedition from Harvard University during the early 20th century remains one of the last major foreign scientific ventures to remove large specimens from this region. Since then, many of the most important discoveries have begun not with large institutional campaigns, but with ordinary people paying attention to the ground beneath their feet. The record they continue to uncover is astonishing. A pearl preserved across deep time, a marine reptile whose remains transformed into gemstone, a predator carrying evidence of its final meal, a fish preserving the marks of an ancient attack, an ichthyosaur caught in the act of giving birth, a moment frozen within stone long before human beings existed. Each discovery broadens the picture, yet none feels like a conclusion. The remarkable truth is that the overwhelming majority of the Eromanga Sea remains hidden. Beneath the red soils and weathered surfaces of the Queensland Outback are layers that have not yet revealed their contents. Countless fossils almost certainly remain enclosed within stone, untouched since the age when the inland sea occupied the continent. Some may represent species unknown to science. Others may preserve behaviors, ecosystems, or biological details that have never been observed in the fossil record. Their existence is not speculation born from imagination. It is a simple consequence of scale. The ancient sea covered an enormous area. Only a minute portion of its remains has been exposed, discovered, collected, and studied. Every season of erosion reveals new fragments. Every storm reshapes a surface somewhere across the basin. Every passing year creates another opportunity for the past to emerge. And so, the Eromanga Sea lingers in an unusual state, gone from the surface world, yet still present within the rock beneath it. A hidden ecosystem larger than any museum collection, scattered across thousands of kilometers, which is about 621 miles for every 1,000 kilometers of remote country. A place known through fossils, yet only partially known. A world that continues to reveal itself one stone at a time, leaving the impression that the deepest parts of its story are still resting beneath the dust. There is a temptation to look at the Australian interior and imagine that it has always been this way. The broad horizons seem timeless. The weathered stone appears settled into its final form. The red earth stretches across such immense distances that permanence feels built into the landscape itself, as though the continent has reached a finished state and simply remained there. Geologists see something different. They often describe Australia as the ancient one, a continent whose surface has escaped the repeated cycles of mountain building that transformed many other parts of the world. Across vast spans of geological time, large portions of its crust remained comparatively stable, while other continents were folded, uplifted, fractured, and rebuilt. Much of Australia endured with remarkable continuity. Yet stability and permanence are not the same thing. Beneath the appearance of constancy lies a history of extraordinary change. The country that now supports deserts once rested beneath seawater. Before that, different environments occupied the same ground. Forests spread across regions that would later become barren. Wetlands expanded and contracted. Estuaries formed where dry plains now stand. Ancient glacial conditions altered landscapes that today experience intense heat. The modern desert is not the defining condition of the continent. It is only the latest expression. If a visitor could move backward through geological time, the transformations would seem almost impossible. Familiar landmarks would vanish. Coastlines would migrate across the interior. Rivers would abandon old courses and establish new ones. Entire ecosystems would appear, flourish, and disappear. What seems permanent from a human perspective becomes fleeting when viewed through the deeper chronology of Earth. The gemstones scattered through parts of the Australian interior provide a remarkable example. In places such as Coober Pedy and Lightning Ridge, miners extract opal from rocks that owe their existence to ancient marine conditions. The silica, sediments, and chemical environments responsible for creating these stones originated within systems linked to the long-vanished inland sea. Every fragment of precious opal carries that history within its structure. The colors that flash through the stone are not separate from the ancient ocean. They are consequences of it. Long after the water disappeared, chemistry continued its patient work underground, transforming sediments and fossils into gemstones that would one day emerge beneath a desert sky. The relationship is so intimate that the boundary between sea and stone begins to blur. The ocean vanished, yet portions of it remain preserved within minerals formed from its legacy. A similar continuity exists within the mound springs, scattered across the interior. For at least 65,000 years, Aboriginal and Torres Strait Islander peoples have maintained connections to many of these water sources. Generation followed generation. Stories were carried forward. Knowledge remained tied to particular places. Across that entire span of human history, the springs continued flowing. Yet even that astonishing duration represents only a small chapter in their story. The sandstone layers guiding groundwater movement were established long before human beings appeared. Water entered the subsurface through geological systems already ancient by the time the first people arrived on the continent. Some of the water emerging today may have begun its underground journey before our own species evolved. A spring, therefore, becomes something more than a source of water. It becomes a meeting place between different scales of time. Human memory reaches back thousands of years. Geological memory reaches back millions. Both exist together in the same flowing water. Perhaps that is why permanence becomes such a difficult idea to define. Mountains erode, oceans withdraw, forests become deserts, deserts become seas, species appear and vanish, even continents drift from one configuration to another. Nothing truly stands outside change. What we call permanent is often only a process moving too slowly for ordinary observation. A coastline held for a moment, a spring flowing through an age, a desert occupying its turn in a sequence stretching far beyond memory. The ancient landscape endures, yet everything within it remains in motion, following rhythms measured not in lifetimes but in worlds. A map can make a landscape appear permanent. Lines define coastlines. Colors separate deserts from forests. Rivers seem fixed. Mountains appear settled. Looking down from such a distance, it becomes easy to believe that the world has finally arranged itself into its proper form. The story of the Eromanga Sea suggests something very different. The driest inhabited continent on Earth once held a cold inland ocean stretching across its heart. Waters occupied regions that now support cattle stations, mining towns, highways, and endless plains of weathered stone. Places separated today by immense distances were once connected by currents moving through a submerged continent. Within those waters lived creatures that seem almost imagined when viewed from the modern world. A predator carried a skull longer than many automobiles and hunted other marine reptiles that shared its domain. Long-necked swimmers crossed the sea carrying rounded stones gathered from distant shores, sometimes transported as far as 300 kilometers, which is about 186 miles, from where they were eventually discovered. Above the water, enormous flying reptiles drifted through ancient skies with wingspans approaching 5 meters, which is about 16.4 feet, surveying a landscape that existed roughly 100 million years before the first humans appeared in Africa. Yet the most remarkable part of the story is not the creatures themselves. It is what happened after they were gone. One marine reptile settled into sediment at the bottom of the sea. Over immense spans of time, its bones dissolved away. Mineral-rich waters entered the spaces left behind. Chemistry proceeded with extraordinary patience. The skeleton became gemstone. Within its ribcage remained traces of a final meal, preserved alongside the stones carried inside its body. Much later, people would work together across Australia to ensure that this fossil remained whole rather than being broken apart and transformed into jewelry. Elsewhere, discoveries emerged through chance rather than design. An avocado farmer noticed unusual remains and helped reveal a creature unknown to science. Fossils appeared in paddocks, creek beds, and weathered outcrops. Fragments of an inland ocean surfaced in places where no ocean existed any longer. Explorers searching for water crossed the same country carrying a boat, convinced that a great inland sea awaited them somewhere beyond the horizon. They endured extreme hardship in pursuit of a body of water that had vanished tens of millions of years earlier. Beneath their feet lay an enormous groundwater system created by the geological legacy of that vanished sea. Yet the technology required to reach it remained beyond their grasp. At the same time, Aboriginal and Torres Strait Islander communities maintained enduring relationships with springs fed by ancient aquifers. For at least 65,000 years, people returned to these waters generation after generation. The springs flowed before recorded history. They continue flowing today. Perhaps that is the lesson hidden beneath all the fossils, gemstones, and geological layers. Landscape is not a noun. It is a process. The continent has never stopped changing. Coastlines migrate, basins deepen and rise, oceans advance and retreat. Water becomes stone, stone becomes dust. What appears permanent is often only a brief interval within a much longer sequence of transformations. Even now, the legacy of the Eromanga Sea remains active. Beneath outback Queensland, ancient sandstone continues holding groundwater that moves through pathways established in deep time. Springs still emerge from the earth. Fossils remain enclosed within rock, awaiting discovery. In a museum gallery, an opalized marine reptile rests with the remains of its final meal preserved within its rib cage, just as they have been for approximately 115 million years. The sea itself is gone, yet its presence persists in groundwater, in gemstones, in fossils, in stories, and in the shape of the continent. Far below the red dust, beneath towns, roads, and open country, the memory of that ancient ocean remains woven into the foundation of the land. It is not somewhere else. It is underneath everything.